So we're talking about surface, area surface revolution. So if I'm looking at this equation, and I want to find out basically what is the surface area is what it's looking at. And we're going to revolve around the x-axis, so everything's in terms of x. If we were going to revolve around the y-axis, everything would be in terms of y. Okay, so we'd want everything over here to be in terms of y. This is my radius. So basically, unless it's something weird, let me draw it. I come over here, and I'm going to draw this, and I'm going to look at the area from 0 to, we'll say 0 to 1. So 0, 0. If I plug in 1, I'm at 1/3. So we'll say this is 1/3. So it's going to look like this. Okay, so if I take this and spin it around, we're kind of really, oops, you can see it. Spin it on the x-axis. We're really kind of getting the outside of that trumpet. Okay, or it looks kind of like the outside of a trumpet. We wouldn't really have a hollow center. Okay, so my radius here is just my function value. So it's just this. So we're going to take our derivative again. So if I bring the 3 down, so 1/3 times 3 is just 1, so I'd have x squared. Okay, so let's plug it in. So I've got 2 pi, and I'm going from 0 to 1. Got my 1/3 x cubed, square root of 1 plus my derivative squared, so x squared squared would be x to the 4th. Alright, so if I'm looking at this, I'm going to pull out that 1/3. So I have 2 over 3 pi. Let's let this be our u. So if I say u is equal to 1 plus x to the 4th, my du would be 4x to the 3rd. Notice I have an x to the 3rd, so that's nice. So I'm going to divide by 4. So we should divide this by 4. So that's going to make that a 12. Okay, so my du, my 1/4 du is there. I've got the square root of u. So again, this is 1/2 power, so I'm going to take the antiderivative, I'd add 1 to it. So this is going to give me 1/6 pi u to the 3/2 over 3/2. Let's find our endpoints. If I plug in 0 here, that's going to give me a 1. If I plug in 1, that's going to give me a 2. Okay. And so let's see, I flip that and multiply. That's going to give me pi over 9. Let's see if I plug in a 2. So I've got 2 to the 3 over 2 minus 1 to the 3 over 2. And so you've got pi over 9. That's going to give me 2 root 2 minus 1. Oh, there's slow. You see it. And so that would be our surface of revolution. So not too bad. It's very similar to arc length. Okay, the last thing that we talked about in Chapter 7 was, let's put that away, work. Okay, so work, typically our formula for work is force times distance. How much force you can have, how far you can have to take it. So our formula, if our force is not constant, would be here. So our force formula times our distance, so my dx would be my distance, over my interval. Okay, and so we're going to use that. One rule we have is what we call Hooke's law, which is if you're using a spring. So Hooke's law. And say we have a force of 20 pounds to stretch 1 inch. Okay, we're going to stretch it 9 inches. So let's stretch 9. Oh no, 20 pounds to stretch 9 inches. To stretch 9 inches. Okay, and we want to know how much work. To stretch 1 foot. 1 foot. Okay, now Hooke's law, we say force is our constant of variation times our distance. Okay, so we need to know what is our constant of variation. How much, if it's going to take 20 pounds to stretch 9 inches, how much is it going to stretch this? Now, it's not really constant, so we can't really set a proportion 9 to 20 equals what to 12. But we can, well, our constant is, we can do that for a constant. So we can say our force is 20, our constant times my distance. Okay, so I'm using this to find out what my K is. So I have 20 over 9. Okay, so this is my constant, so it's going to take that much per inch. So if I'm doing 1 foot, that's 12 inches. So I'm stretching from its natural position to 12 inches. And so I've got 20 over 9 times x dx. So if we take our antiderivatives, this is 20 over 9 x squared over 2 from 0 to 12. So it's going to give me 10 over 9, 12 squared. Okay, so that's going to give me what? 12 squared. So 144 times 10 divided by 9. It's 160. And that's going to be in inches. Pounds per inch. Pounds per inch. Okay. Another one, say we have a cylinder. And we are, you have a cylinder, it's holding water or holding gravel or anything that one may be coming out. So say it is 5 feet tall and my my radius is 2. Okay, so now say I've got water in here and say it's full, but we're pumping out of it. Okay, so my height is going to be changing according to this. So when I very first start, it's going to be 5, and then as it comes down, it's going to be whatever that, however far it's down from 5. So for volume, you're looking at area, so I've got pi r squared h. Okay, now my radius is constant all the way down to the bottom. It's not kind of coming in, you're not looking at a cylinder. So my radius is 2 for the entire thing. But my height is changing. Okay, so my height is changing according to this. So at 0, my height would be 5, and 1 foot down would be 4, so it's going to be 5 minus whatever my x value is, or we could say y. We can do it in terms of y. Okay, so say my force is 9,800 pounds, okay, per foot. And I'm going to empty the whole thing out. So we're going to go from 0 to 5. I've got 2 pi, 5 minus y, dy. And we could use an x, it really doesn't matter. And so we've got this times 2 pi. I can go ahead and pull 2 pi out. Let's take the antiderivative of this. So I have 5y minus y squared over 2. And then just plug in my endpoints and see what that gives me. So I have 25 minus 25 halves, or 25 divided by 2, times 2 times. So it's going to give me 245,000 pi, and whatever our units happen to be. Okay, so let's look at the last thing, and say this last one is if we were pulling a chain up. So say we have a 20-foot chain, and it's held by a winch that's 20 feet in the air. Okay, so the very bottom's touching the ground, and it's 20 feet in the air. Would be the winch. Okay. So say that it's 3 pounds a foot. The chain is 3 pounds a foot, and we want to know how much work does it take to wind up the entire chain. If it holds, so let's see, wind up entire chain. And it holds a 500-pound weight at the bottom. 500-pound weight at the bottom. Okay. All right. So if we look at this, we've got, it's going to take 3 pounds. Sorry, I can't talk. We're going to wind up the entire thing. So we're going to go from 0 to 20. Each foot is 3 pounds. Now, the number of feet, and since we're winding it up, it starts off with 20 feet, and each foot we wind up, it's going to decrease by 1. So we're going to do the same thing. So we're going to say 20 minus y dy. And we take the antiderivative of that. Now, at the end, we're going to add 500 pounds times 20 feet. Okay? So here, if I take the antiderivative, that's going to give me 60y minus 3y squared over 2. I can 0 to 20 and then add 1,000 to it. So this, if I plug it in, I've got 60 times 20 minus 1.5 times 20 squared. It gives me 600. So I've got 600 plus 1,000, so 1,600 pounds, or foot-pounds. Okay. So that is all of Chapter 7 that we talked about. And it's basically just kind of looking at your formula, setting it up, taking the antiderivative. All right.